Okay, so welcome back to the second lecture. So now let's study, we have seen the black hole puzzle in some kind of an outline cartoon picture. We had a horizon, we put particles inside, outside, and so on. Now let's learn a little bit more about the black hole in technical terms. Okay. So we'll begin by understanding the structure of the black hole, and then we'll talk about the whole idea of entanglement in a little more mathematical way, and then we'll understand why the Hawking puzzle is really such a robust and rigorous puzzle. Okay, so here's the black hole now. It is described by what's called the Schwarzschild metric, and this is the Schwarzschild metric. So if you have ever seen the black hole metric written down, you probably have seen it written down in these coordinates. So in flat space, the metric would just have minus dt square and then plus dr square, and that's the flat space metric in polar coordinates. Now we have these extra factors, and I have put G and C and so on to 1, and so then you can see the metric coefficients here get into trouble when r becomes equal to 2m, which was the radius of the horizon. So at the horizon, the coefficient of dt square vanishes, the coefficient of dr square actually diverges, and you can see that this metric holds only outside the horizon. Of course, our interest is in what happens at the horizon and what happens inside. So when you write the solution in this form, you don't quite understand that. And so our goal is to actually understand what is happening at the horizon and inside, because we want to see the outside, the horizon, and the inside all at one time. Okay, all in one way all together, and this way of writing the metric somehow can't do that. For r greater than 2m, this is all a well-defined metric, but r equal to 2m, which is the horizon, you can see the coefficients are getting into some trouble. Okay, so but anyway, if we keep looking at this metric was found by Schwarzschild as a solution to the vacuum Einstein equation. So if we have vacuum everywhere except maybe at a point in the center, anywhere here the Einstein equations are solved by this metric, and this is the analog of the normal gravitational potential minus gm over r that you have in Newtonian gravity, the metric of the potential of a point mass. Well, if you look at this, there's a crucial point that we have to extract from this. We want to know what is a space-like surface. So you might have heard about space-like surfaces. A surface which is time equal to constant is what is called a space-like surface. So a surface which goes in x, y, z directions but not in t is an example of a space-like surface. Why are those so important? Because in quantum mechanics, we give the initial wave function on a space-like surface. We give it psi at all points x, y, z, and then that is enough data to find the psi at a later time, some other time t. So the physics proceeds by understanding space-like surfaces, and so we have to understand where are the space-like surfaces in the black hole. So if you're outside the horizon, it's clear. Outside the horizon, in fact, far away, it's just normal space. So the surface time equal to constant would be a space-like surface, and you can describe your wave function on that. Okay, so for r bigger than 2m, this is space-like. But let's see what happens for r less than 2m. For r less than 2m, this number is actually negative, and so dt square has a positive coefficient and the dr square has a negative coefficient. So now you can see the time component is behaving like a space direction and the r component is behaving like a time direction. So inside the black hole, for r less than 2m, a space-like surface is now going to be given by r equal to constant. So all the physics of the black hole actually comes from this one observation. So is this clear that if you want to make a space-like surface on which a complete wave function has to be defined, outside the black hole, time equal to constant, different values of r, theta, phi give you the space things, but inside the black hole, r equal to constant, but all values of t, theta, phi define a space-like surface. Okay? So in fact, if you have to draw the whole thing, this is just a schematic cartoon picture. This is the r direction, this is r equal to 0, this is r equal to 2m the horizon, this side is r equal to infinity. As we said, outside the slices will look like t equal to constant, they are space-like slices. Inside the horizon, the r equal to constant are space-like slices, and if I join them smoothly like this thing actually is a complete smooth space-like slice. So this is very interesting, because now you see that inside the black hole, you thought there was only a finite amount of space. Maybe the black hole had 3 kilometer radius, you'll say, okay, there's a 3 kilometer ball in there. But actually inside the black hole is an infinite amount of space. This is now the spatial slice. Just like this was space, this is space. And I can just keep going down at r equal to constant. Let this be r equal to m, which is halfway between 0 and 2m. Nothing bad is happening there. R equal to 0 is a singularity, but I'm not going near r equal to 0. I can stay at r equal to m and make this infinitely long, and this is all space. Okay? That's the magic of the black hole. There's infinite amount of space hiding inside the black hole. Okay, and this will actually play a crucial role in the Hawking puzzle. Okay? So you can also draw the whole thing. You don't need to know this if you don't know it before. You can put the whole thing in terms of a Penrose diagram, and if you do that, those slices I drew are actually smooth slices like this. They are space-like slices, and anyway, their length actually can become infinite, as we already saw on the previous picture. Okay? So what we see from there is that these slices, let me just go back to this picture for a second, the difference between these space-like slices and the space-like slices in this room are going to be crucial. Because in this room, the slices are t equal to constant. There's no metric here. The metric is just flat. So one space-like slice and the one at a later time are identical. Okay, so if the space-like slices are all identical, on this slice, suppose I start with the vacuum state. Then everything is time independent. If I go to the next slice, what will I get? Again, the vacuum. So the vacuum remains the vacuum. Okay. Now suppose you have some general situation where on this slice you had the metric was just maybe some flat metric, but suppose the metric was changing, some general relativistic process was happening, and on the next slice the metric was different. Okay, it doesn't have to be a black hole. It could just be that there were some two stars and they moved closer together. Then the metric will change. Okay, so on the initial slice, suppose you took the vacuum state. Then on the next one, because the metric has changed, there will be some other vacuum. What is a vacuum? A vacuum has its own quantum fluctuations and so on. But if I change the metric, it's a different vacuum state. It will have its own quantum fluctuations and so on. But if the metric changes, the vacuum which I had here may not evolve to the vacuum which I have there, because that guy needs its own vacuum fluctuations. So whenever the metric typically changes, some particles are created, because some of the virtual fluctuations actually end up becoming real particles. So typically that's the point. If the metric is actually going to be constant, it doesn't have to be flat space. Even if you have a star which is just standing there, the metric is constant. The space-like slices may have some structure, but later time they have the same structure. So once things are stabilized to a vacuum on one slice, the vacuum will persist. But if the metric is changing, then typically particles will be created. That's what Hawking found. Okay, I mean that was known before Hawking, but that will also happen in the black hole. But now what we are finding is that even though the Schwarzschild metric which I had here, it looks to be time independent. You can see the coefficients don't depend on time. So at first you think it might be a time independent situation. Why should it create any particles? But actually it's not time independent, because this form of the metric holds only outside the horizon. And if you go inside the horizon, well, time and space interchange roles, and we saw a space-like slice was drawn like this. But a later slice, later means if I go up in time, it's actually going to go like this, and the later slice goes like this. Okay, so you see all the slices are not the same, and if you want to see what the difference between them, actually the later ones are becoming longer. See, this one is like this one goes up to here the same, then it stretches more, and then comes out. This one stretches even more, and then comes out. The slices are stretching. Okay, and that's why once you have a black hole metric, you cannot make all the space-like slices the same. You can make one space-like like this, but the next slice has to be different in internal structure. And so even though the metric looks time independent when you see only the outside part, you cannot do any slicing of that space-time in such a way that all the slices are the same. This is the crucial point, and this is why a black hole actually keeps producing particles. We had seen it already in schematic way by saying negative energy here, positive energy here, but general relativity, when you come down to it, you're really only going to see the slice and the vacuum state on the slice and how the vacuum state evolves. If the slice changes structure, you won't be surprised to think that it might create some particles. For now, you can see the slices keep stretching, and that's why the particles are actually created. Okay, so as we said, this is the summarizes what I was just saying. The stretching of slices leads to particle creation. In general, any change in the geometry leads to particle creation. You could have a star of some radius. It shrinks and stabilizes at some smaller radius, maybe a star collapsed to a neutron star. What you would do is solve the field equation in terms of Fourier modes. We're not actually going to do this. So if this is not familiar to you, you don't have to worry. And then if you actually have a vacuum state, it's the one which is killed by all the annihilation operators. But if the structure changes, then in fact you'll get a new vacuum state, because it's killed by different annihilation operators, right? And so the vacuum which you had before is not the vacuum which you have after, and so the quantum state will actually have some particles. So again, I'm drawing this schematically. If you had some curved state here, and then you're actually going to create some particles when you start changing the metric. If you start changing some metric around here, then particle pairs will be created. So let's get some rough idea of this kind of particle creation. It's called particle creation in curved space. Whenever a metric is changed, particles are created. Okay, so this is a general field called particle creation in curved space, but we can learn some general scales of creation without actually doing the full details of the calculation. So suppose you have a scale r, suppose it's a star, so it's a scale of maybe a few kilometers, let's say, like a tight neutron star, and you change the metric to something else by order 1. Okay, so you make some change of metric for order 1. You're not making a black hole or anything. So it changes in a time of order r by order 1. The metric changes order 1, the coefficient change by order 1, and the spatial range is also r. Well, in that case, how many particles are you going to create? I'm looking for a pure number. It can't depend on r. The answer is number of particles I'm going to create is order 1, maybe 1 or 2 pairs. So if you take a 3 kilometer metric region which changes in a time scale also of the same order, light crossing time of 3 kilometers by order 1, it creates of the order of 1 particle pair. What will be the wavelength of the created particles? There's only one scale in the problem, r. Okay, so 1 particle pair whose members have wavelength of the order of r is created when a space-time region of size r changes by order 1. Okay, that's the basic physics of particle creation in curved space, and that's all we need to know, except for one more thing. If you create a particle pair, then typically the 2 members of the pair come out in entangled state, and that I have written like this. So if you think in terms of spin, if this guy was spin up, this would be down, this would be down, this spin up, because they came out as an overall singlet. Okay, this is all we actually need to know about particle creation, and now we can apply that to the black hole, because we've seen in a black hole the slices keep changing. One slice could be like this, the next one will be stretched to be longer. What is the scale of all the stretching? If you look at that picture, the only scale comes from the horizon radius, that is 2m. Okay, so if for the length scale I put 2m, then after I'll be just creating particles, and we'll just see the scales of particle creation. We just need to know all that schematically. So the reason the particles are created is like this. If you have a horizon here, then geodesic just at the horizon, just stay stuck there. That's what we had seen. If you're there, you're just stuck there. If you are just outside, you can go out. If you're inside, you go in. So if you had a particle mode here, you can see the particle mode keeps getting stretched. So we had seen that there's just another way of drawing the same picture. If you have a particle wave mode here, the points outside ultimately go out. See, points here ultimately go out. Light rays here are going out, while light rays inside are just going to go and fall in. So there's a tearing apart of geodesic. So geodesic which is at the horizon stays there, but just outside goes out, just inside it goes in. So this spatial region here is actually stretching. This middle point stays here, the inside point goes here, the outside point goes here, the inside part goes here. So you can see the stretching of wave modes happening. So any particular wave mode here keeps getting stretched. You can see how particle modes are now changing in structure, and that's what leads to the particle creation. So that's what Hawking found. This was again our slices. I've drawn the slice like this. So you start with a slice which is maybe a slice like this at an earlier time, and if you have a wave mode in there, as you go to a later time, it stretches out to some wave mode which has some crazy structure, and if you analyze that wave mode in terms of particles using quantum field theory, then you see this particle pair creation. So I'm not actually taking you through the details of this. I'm just putting a few words here to show you how the technical calculation is done. You simply take the quantum field theory description of particles, which is that you expand everything in wave modes, the analog of the e to the I kx minus omega t. Then you see how the wave modes evolve. And because the slices are stretching, the wave modes evolve in a way that if you started with the vacuum, after some time you won't have the vacuum, and you basically get a particle created here, and you get a particle created here. But all you have to really do technically is to follow the evolution of the wave modes in this particular metric where the slices are stretching. Yes?
Sorry, the Hawking's original calculations didn't care about any pair production or something like that. It was just a comparison between the initial state, initial vacuum state, and the final thermal state.
Well,
is there a major difference between these two interpretations?
Not really. Actually, Hawking really did this secretly. His paper was very brief, so he only kept the part which he wanted. So it's a little difficult to read that paper, but what he did was, later on, quickly written out in more detail in other papers. And this is what he really did. He took a wave mode which was, it's important to start with a wave mode like an e to the I kx minus omega t, like you do for in this room for doing quantum field theory. Part of the wave mode is inside the horizon, part is outside the horizon, so it crosses both sides of the horizon. Then he followed the wave modes, and this part of the wave mode evolves out, like here. This part of the wave mode goes in, and this part just stays here. So you can see that even if this was an even wave mode with, like a sine wave with equal periods between all the waves, after some time they're not equal periods. Okay, they become like this. He only focused on this part and said, if you look at this part, it doesn't have only positive frequencies, now it also has negative frequencies. And once you mix positive and negative frequencies, the positive frequency part multiplies A, the negative frequency part multiply A dagger. So if here you had the vacuum, so that it was killed by all the A's, now it's killed by a mixture of A's and A daggers, so you have particles. So he only focused on this part, but the real thing is the other part is also there. He looked at this part and said that's not in a pure state. The reason that's not in a pure state is that this guy is entangled with this. Okay, so he didn't write it all out, but really this was in the paper, the 1975 paper. So anyway, this was all just supposed to be cartoon, so there's not that much you can learn from it. Let me just extract from it the part which I need, and then we can just work with that. And so the part that we need is, again in the picture, the space-like slices are keeping on changing with time because they have to become stretched, they have to be stretched to longer things as we go to later slices. The stretching actually creates particles if you do the quantum field theory properly. And so what is sitting on the slice? First, all the black hole, the stuff that fell into the black hole to make the mass, that was to make the black hole or the matter that fell in. That will also show up on every space-like slice, because space-like slice is complete. It has to capture all the matter that's in the problem. So the initial matter is sitting somewhere. That doesn't really bother us right now. We are interested in the fact that if we had the vacuum state here, when the slice is stretched, it won't be the vacuum. It will actually have an entangled pair, which you'll write schematically in this form to talk about the entanglement. If you go to the next slice, there's further stretching going on. So then when the further stretching, this particle is here, this particle is here, the region here stretches, and because it stretches, it creates a new particle pair, this and this. So the old member of the pairs are here and here, they are entangled with each other, and here's a new member of the pair, and they are entangled with each other. So this is the entire pair production process. Yes?
When we are writing the state of the particle outside the horizon, we are using the time evolution operator.
Yes?
And the meaning of the time and space changes inside the horizon.
Yes.
When we are writing the state of the other particle.
Yes, the inside particle, yes.
How are we writing this?
Okay, very good question. So when I'm writing this, I have not been precisely writing any states, I was just drawing cartoons. But what I'm supposed to be doing is I set up a new coordinate system in which this is space. You could call this some kind of X in your new system, but the X starts from here and goes here. Okay?
Space evolution operator. I'm using some kind of, am I using some kind of space evolution operator?
No, it will be all normal evolution. Because this is a space-like slice, it just looks bent, but that's just because of the way I have drawn it. But this is all a space-like direction, right? So I will choose some coordinate that runs from minus infinity to plus infinity along this, right? And normal to this, like this way, and perpendicular to it this way, is time. So here time goes this way, here time goes this way, here is this way, here time is this way, and so on. So perpendicular to this one, imagine time. So if I want to draw the wave function of this particle and say it's like a normal particle, at this point, let's say think of this as space and this as time, and in that language, it's a normal particle. So it just looks crazy in this picture, because in this picture, the embedding makes it look like it sort of went in. But really, wherever I'm drawing it as a red line, that is space, and perpendicular to that is time. So at any local place here, you could set up a local orthonormal frame where this looks like space and this looks like time. It's only the embedding which makes it look sort of tilted. But the embedding doesn't matter, right? It's the intrinsic physics. This is space and this is time. And in terms of that, this is a completely normal particle. Okay. But the energy of this as seen from infinity, that is negative, because then I have to really worry about that fact that this is tilted compared to what is time here, and that tilt makes it negative energy. So when you talk about energy, what we had asked before in the morning, why does it have negative energy? As a local particle here, well, this is space, this is time. Locally, every particle in a normal region has to have positive energy. It does. It's just that using this as time, it has normal positive energy. But if you think in terms of the time at infinity, it actually has negative energy. And what is conserved is the energy as compared to infinity. And from that point of view, it has negative energy. Does that answer what you were asking? Okay. But then this is the entire structure we'll be interested in. Where are the particle pairs created? This part of the slice is not changing. Nothing much is changing here. This part is also not changing. As you go to the next slide, this is earlier time, and later time. As you go to later times, what is happening is, just think of this as one space-like slice like this. Okay, this looking tilted is only because of the way it's drawn. It's just one space-like slice. At the next time, it's not the same slice. You leave this part, let's say the right 1/3 as it is, the left 1/3 as it is, take the middle third and stretch it. Then when you do that, one particle pair will appear here. Okay, now at the next step, again, take the right 1/3, leave it untouched, left 1/3, leave it untouched, take the middle part and stretch it. Well, the particle member which had appeared here will just go further out. There, the particle member which was here will go further out, but nothing else will happen to it. But in the middle region which I stretched, another particle pair will come, and that is this pair. And so on the complete space-like slice, now you can see a little bit more about where the pairs are coming. Okay, it's still a cartoon picture. We don't actually need the calculations, but again, to see the entanglement, this guy's entangled with this. They're in like spin up, down, minus down, up, or you can schematically write it like this. And then this guy's entangled with this, and so on. Okay, so let's get all the scales of Hawking radiation. We can understand the physics very easily in terms of scales. Okay, there's only one length scale in the short shell metric. That's the radius of the horizon. Okay, so the emitted quanta have a wavelength which is of order r. So if somebody asks you, tell me something about Hawking radiation, what's the wavelength of emitted quanta? It's r. If one quantum comes now, after how much time does the next quantum come? Well, delta t. I'm using units with c equal to 1. So space and time have the same units. What is delta t? There's only one scale, r. So once one particle basically goes out, the next particle starts. Okay. So how many quanta do you emit? From this you can find everything. The total mass you have to emit is capital M. Again, it's mc square, but c is 1. And the energy of each quantum, if the wavelength is r, the energy is 1 over r. So the number of particles you're going to actually emit, okay, I just put the g, r is 2 gm. I just put all that in here. You get a gm. If you put in terms of Planck masses, it's m over m Planck whole square. So you can compute how many particles you will emit, because each particle has energy 1 over r. Because the wavelength is r, total mass you have to get out is m. So easy way to compute how many particles. You can see a big black hole will emit lots of particles. The mass for the sun is 10 to the 33 grams. M Planck is 10 to the minus 5 grams. So this ratio is 10 to the 38. And so when you square this, it's 10 to the 76. So it will emit that many particles, particle pairs, before it is gone. Okay, so everything about the black hole you can just see from scales, and this is the only scales in the problem. This is all you need to know about Hawking radiation. Okay, so again, in terms of questions, you have to ask somebody about the model of the black hole. Do you have the vacuum around the horizon? If not, why not? If you have the vacuum, do you get entangled pairs by stretching? Because you can just see, you're just going to get stretching of slices. If you stretch a slice, the vacuum has to change. And particle pairs will be created. Something so basic in quantum field theory. This is what you do when you just quantize a field on a space, and you shake the space, the pairs come out. If you're not getting particle pair production, why not? The physics is so simple. Okay, so the reason that string theorists I had mentioned were not so worried about this problem was because they actually made a mistake. By they, I should say not everybody, but so some people were worrying about it all through the years, but many people were not. And the reason people were not worried about it was because of something called the belief in small corrections. So let's talk a little bit about that. So as we said, what's the solution in string theory? And so one thing you could have is that we said the slices are stretching, and Hawking did this, right? He saw the modes were stretching. I had drawn it in red lines, and those are red lines here. But of course, Hawking did a leading order calculation. When you do a calculation in the beginning, you have to do some approximate calculation, and you're done. He saw the entanglement growing. We already saw how the entanglement was growing. But every time a new pair comes out, there's more entanglement. But then there could always have small corrections. So the actual wave might be evolving according to the dotted blue line. Where would the small corrections come from? Well, from anywhere, we don't know, right? There could be some quantum gravity effects we don't yet know, and so there could be a small change in the state of each particle pair. That doesn't look hard to believe. In fact, it's almost certain that should be there. Well, so very small corrections can come from any source. Why should we care if they are small corrections? Why should we stop believing in Hawking result? Well, the corrections will be very small, because after all, around the horizon we expect to be just empty space, and you know how when slices change in empty space over these large curvature distances, we think we know the physics. Okay? The number of emitted particles we saw is very big. The number of particles emitted from a solar mass black hole was 10 to the power 76. So what people started wondering was, suppose there's a correction to each pair of 10 to the minus 76. 1 part in 10 to the 76. That's very small, right? So suppose there was a minuscule correction of that order to each pair coming from some quantum gravity effect. But then there are so many particles being emitted. Maybe the little corrections that are coming in there will remove all the entanglement problem. Right? If there's a small number somewhere, like the corrections, and there's a big number somewhere, sometimes small number can trade against a big number, and maybe the entanglement goes away, and maybe Hawking made a mistake, he did a leading order calculation, but the subleading order, normally you wouldn't care about subleading order too much in a problem, but if the number of particles is very big, there are many subleading corrections, and maybe the subleading corrections outweigh the leading corrections, and this is what is called subtle encoding. There could be some subtle changes to each pair, and in the end there is no problem. It looks fairly persuasive. Right? And we have to actually see, is it true or not true? Because this is true, there was never any information puzzle in the first place. As we see in the end, actually this is not true. You cannot trade the small corrections for the large number and hope to get away with the problem. But this is important to understand, first because it removes a lot of solution that people proposed for this puzzle. Okay? String theorists and also non-string theorists. But also it will tell us that the puzzle is completely rigorous then. We really have a puzzle to solve, because if small corrections can't help us, we need to get large corrections at the horizon, which means we need to completely change the black hole. And that's a very serious job, because the black hole is a big classical object. But if this is true, it will tell us we need to completely change the black hole to get out of this puzzle. So let's focus on trying to understand this. It needs a little bit of understanding of entanglement, but in the end all the steps are very simple. So let's just learn the relevant math and then go with it. So again, this is the picture we'll be working with. So now let's try to put some math over this. Again, these are the space-like slices. As they are entangled, entangled, the entangled pair I've drawn like, let's call the first pair B1 and C1. The mode outside I'll call it B, the mode inside I'll call it C. So this particle is called B1, this is called C1. And as I said, the B1 moves out, the C1 moves in, and when the slice stretches, and a new pair appears, B2 and C2, and these guys are entangled with each other, these guys are entangled with each other, and so on. And then we can write the amount of entanglement. I'll just do that in a minute, but first let's write the entire state on this complete space-like slice. As we said, if you have a complete space-like slice, you can write the entire quantum state on it. What's the entire quantum state of the entire system? I'll call that capital psi. There's first the state of the matter, whatever fell in to make the black hole. That goes to the earliest time, so it's at the extreme left on the space-like slice. That's there. It won't have any role to play in everything else, but it's there, so at least let's write it there. And then we have this particular pair. I'm writing it on this last slice, let's say. So this particular pair, C1 and B1, are in this entangled state. So state 0 for C1, state 0 for B1, plus state 1 for C1, 1 for B1, and I've even normalized the state for you here. And then B2 and C2 are not doing anything with B1 and C1. This was a completely independently created pair, so they are in this state. So we directly tensor the state of this with this, and this is the complete state on this last slice. Let's see if this notation is clear with everybody. If there are questions about this, since I'll be using this notation later on, let me see if there are any questions. Okay, so this is the notation, and then let's see how we talk about entanglement. So on this slice, there are no entangled pairs. So entanglement of the outside with the inside. Outside is whatever is outside on this slice, whatever is inside, there's no entanglement. We'll talk in a minute about how you measure entanglement, but anyway, you can believe at this moment there's no entanglement. When there's one pair, we said the entanglement will be log 2. Why log 2? Because when it's state 1 times 1 prime plus 2 times 2 prime, when there are two pieces in the sum, we said the entanglement is log 2. So on this slice, there's one pair, so it's log 2. On this slice, it's actually log 2 from this pair and log 2 from this pair. So it's 2 log 2. You can see how it's growing like that, right? Because when you have both these slices, there are four possibilities. There could be 0 and 0 with 1 and 1, or 0 and 1 with 1 and 0, or 1 and 0 with 0 and 1, or 1, 1, 0, 0. There are four states outside, and there are mirror 4 states inside. So you can see if you write this whole thing out, by expanding there are 4 terms, and so then the whole thing will become log of 2 squared, log of 4, which is 2 log 2. So exactly as we were saying, entanglement measured by each state inside times each state outside, and so the number of terms in that sum is basically the log of that is the entanglement. As you can see, the entanglement is actually growing as I emit more particles, and as the number of particles emitted, log 2 plus log 2 plus log 2 is 10 to the 76. The total entanglement of the outside with the inside, all the green particles, the red particles, will become a huge number. Okay. So is everybody comfortable with the picture? Because we'll just have this picture here for the rest of the lecture. And what we are going to try to prove is, if we make small corrections to the states of these pairs, by making slight changes to these guys, even though the number of these guys will actually become very big, there'll be 10 to the 76 of these guys in there, doesn't matter what little things I do to them, I cannot actually remove the entanglement. That's what we are trying to prove. So again, here's the picture in cartoon. If you make small changes, can you remove the entanglement? So how do you make the small changes? Let's make a mathematical model of the small changes. So far it was only a cartoon picture, but now I'll write it like this. This was a state at leading order I had used in my toy model of Hawking evaporation. And so what I'll do is I can add a little bit of maybe the orthogonal state. If I have only a 2 bases 0 and 1, the orthogonal state maybe looks like this. So let me add a little bit of this. But this epsilon k has to be very small because I want to make only a small change. Is that okay? So what is epsilon k? It's a small number because I don't want to make a big change, but it can depend on anything. It can depend on some quantum gravity effect, it can depend on what was the matter inside the hole. If it wants to carry the information about that matter, it can depend on the matter inside the hole. It can depend on all the previous members of the pairs which came out, maybe electron came out before or positron came out before. It can depend on anything. So in a subtle way, we are trying to encode the information of every particle seeing every particle, or every particle which is emitted seeing what was inside the hole, or any other quantum gravity effect. Let's put all of that in these small quantum gravity corrections. And again, epsilon can be very small, even maybe 10 to the minus 76, but the number of particle pairs we are going to produce is e to the plus 10 to the 76. Let's see if that removes the problem. Okay, so at the first step of emission, let's say we do the normal emission because no other particles are emitted. At the second step, maybe, depending on what we had at the first step, suppose the first step we had 0, 0, at the second step we might have a little bit more of 0, 0, a little bit less of 1, 1. See, I'm trying to make little correlations between the pairs. If the first pair was 0, I'm making the second pair, the B2, C2, have a little bit more of 0, 0, a little bit less of 1, 1. And then if in the first step I had 1, 1, I could maybe put a little bit different amount of 0, 0, different of 1, 1. So you can see I can put lots of little corrections in there. How many correction terms are there of this kind? You can see if there are n steps, there are about 2 to the n of these correction terms. Correction terms are whatever come with the epsilons. And so what people were wondering was, like, maybe this is where Hawking made his mistake, because the number of these terms in the sum is 10 to the 76. So if n is 10 to the 76, this is 2 times 10 to the 76 correction terms in here. Okay, and if I take the effect of all those correction terms, it might actually remove the entanglement. So these are the correction terms that we are talking about. Okay. Now let's also see what is the entanglement that we are talking about. So this is the cartoon picture. At leading order, each guy was only entangled with its own partner, like up, down, minus, down, up between this partner. It didn't care about the other guys. But secretly, every guy might care about every guy. And because there are 10 to the 76 of these, that might actually become a big correction, because there are a lot of these, right? Large number. And what's the entanglement we are measuring? Let's draw an arbitrary dividing line at some place away from the black hole. Let's say at 10 times the Schwarzschild radius. Okay, that's good enough. I'm away from the black hole. Everything outside I'll call outside. Everything inside I'll call inside. I compute the entanglement, just a quantum mechanical problem now. I compute the entanglement of everything outside with everything inside. If by the time the black hole is about to go away, suppose the entanglement has somehow magically gone to 0 or close to 0, then is it okay? If the entanglement has gone to 0, then if this thing vanishes, is it okay? Yeah, if this thing is not entangled with this, the overall complicated quantum state of these radiation particles, the whole problem was this was entangled with this guy at leading order, heavily entangled, each guy with his own partner, right? And then if this guy went away, this guy was stuck with no state. But if because of all these delicate correlations, suppose this guy makes some state by itself, whose net entanglement with this guy is 0, then there is no problem. This guy can vanish, it anyway has no energy, now it has no entanglement with anything, and this is left as a state, there's no information puzzle. Okay, so this is what people are having at the back of their mind, and largely also in the string community, because what they were wondering were that, look, we want a unitary theory of string theory, we don't have any remnants, we don't have any information loss because we have to save quantum mechanics. What's the only option left for us? And people thought the only option left is that these subtle corrections, so many of them in number, will remove the puzzle. If this also doesn't work, then we have only one choice left, and that's to actually not have the black hole at all, or to change the whole process by order unity, completely change the black hole, because any small correction is now here. Doesn't matter where the small correction comes from, and so this is a really crucial step for us. So what we're going to do now is to do the math of this and go to this little theorem. How do we actually prove that these small corrections, even though there are so many terms, the many doesn't help? Okay. So before that, we should wonder why people were thinking about these small corrections, why people worried so much about it. And the reason people worried about it is that when you burn a normal piece of coal, then what happens? There also you will get some entanglement. Like suppose here on the surface of the coal, there's an atom, and suppose the atom has emits a photon, and the photon goes out as spin up. Okay, one polarized one way. Then the atom will be left behind and spin down. It could also emit the other way. The photon could go out as spin down, and the atom will be left as spin up. So do you see the entanglement of the radiated particles with what is left behind is increasing? Right? It's up, down, minus down, up. So when the coal emits a photon, then the entanglement of this thing with the coal actually goes up. Then why is there no trouble when you burn a piece of coal and the coal is gone? There's a vacuum here, you only have radiation. Why don't we worry about the entanglement? In fact, if you plot a graph of the entanglement with how much emission is going on, in the beginning, the entanglement is actually going up. You see it's going up because this guy is entangled with this, the next atom will be entangled with its own photon, and so on. But you see, after some time, even the atom which is left behind is going to float away to infinity, because I want the coal to completely burn away, right? That'll be like a piece of ash, ash also floats out to infinity. And then this guy will float out to infinity, so in the end, when there's nothing left here for the coal, you will have the photon and the atom entangled with each other, some other photon entangled with the atom. And if you collect all the guys at infinity, it's just entangled with itself, and this guy can happily go away. So after some time, after the halfway point, when the ash starts coming out, the entanglement of what is outside with what is left behind actually starts going down, and at the end step, there is no entanglement of this with this left here. So when you burn a piece of coal, it behaves that way. And so people were thinking that maybe these subtle corrections in Hawking radiation will take care of things. And even though initially Hawking thought the graph was just going up and up and up and up. But maybe because some subtle corrections, the graph actually goes around like a normal body, and then this guy can go away, and then there'll be no problem. Okay? So this was the reason why people were thinking that this might happen. Okay? And so now we just want to know whether a small correction can actually do this, and whether we can go back to the vacuum. Hawking just thought that it just keeps growing up and up, and what we are wondering is, here's the question mark, can the small corrections make it go up and come down? So that's the question, and now I'm going to go to the theorem. So let me see if the question is clear to everybody. This is good? Okay, so let's just go through the actual small corrections theorem. So how do you actually measure quantum entanglement? So here, suppose you have two systems A and B, and they are entangled with each other. As we said, you can write the total state psi of the two systems as some state of system A times some state of system B, and then you can add up summing over them. Okay? So you can use an orthonormal basis, but there are many terms in the sum. Psi1 times chi1 plus psi2 times chi2 and so on. And if you want to actually make what's called a density matrix, I'll just skip over that because a little bit short of time. If you have these numbers Cmn, you can actually make this diagonal. So the whole thing looks like some number Ci times psi I of A times chi I of B, and just sum over these. That's the way I was mentioning it symbolically before, psi1 times chi1 plus psi2 times chi2 and so on. They don't all have to have the same coefficient C, the same number, they could just have different weight Ci. If you take a state like this, the entanglement is actually then quantified as entanglement of system A with the remainder B is Ci mod square log Ci mod square and summed over all the Ci's that you have. So let's just take a simple example of this maybe on the board to make ourselves familiar with this. So suppose you take a system which is the one we have, 1 over root 2 spin up for the first system, spin down for the second system, minus 1 over root 2 spin down for the first system, times spin up for the second system. So now you can see there are two terms in the sum. So the capital M is 2. Okay. So the C1 is 1 by root 2, and there's a C2 which is 1 by root 2. Right? Psi1 times chi1 plus psi2 times chi2, where C2 is minus 1 by root 2. Okay. So how do I compute the entanglement entropy? I have to take Ci mod square. So C1 mod square is a half, and then I have to write log of C mod square, which is log of a half. There should be a minus sign there, which I think the second line doesn't have. And then from here I get half times log of half. And there should be a minus sign which is missing from there from the second line. It's there in the first line. So then this is what I get. And how much is this? This is equal to minus, well, I can write it up plus half log 2 plus a half log 2. Right? Log of half is minus log 2. So I can write it like this. And so that is equal to log 2. So when you have some simple state like this which has two terms in the sum both with equal weight, the entanglement entropy we said is equal to log 2, and now you can see that answer is giving me log 2. Okay, so this is how you do it. If you just go back to some elementary book on quantum mechanics, you will see that written in there. Okay, but entanglement entropy behaves in a little bit funny way compared to normal entropy. If you have two systems which are entangled with each other, but they're not entangled with anything else, this state is entangled with this, like up, down, minus, down, up, then this state has an entanglement entropy compared to this, for entangled by itself, which is log 2. This guy is also entangled with this by log 2, because this guy is entangled with this guy is entangled with this. But the total system A plus B, well, that is in one state. This is the state. Now that's not entangled with anybody else. It has a definite state of its own. So what's the entanglement entropy of the total system? It's 0. It's not entangled with anybody. So it's very funny. If the entanglement of entropy of A is equal to entanglement of B, the entanglement entropy of the total system A plus B, this means take system A and B together, the total entanglement entropy of this is just 0. Okay. So this is not how the way classical systems behave, right? If this had entanglement entropy A, this had B, normally when you put the two boxes together, you'll get entanglement entropy SA plus SB, it will double up. But here, the total system actually is, because they were just entangled with each other, total system's own entanglement is actually 0. So you can see it behaves a little bit funny, but there's nothing else. It's just ordinary quantum mechanics here, and that's where we are. So can I just ask, can I go for 10 more minutes and stop? Is it okay? What's the time that I need to stop?
Yeah, as you like.
Okay, so maybe about 10 minutes or 15 minutes, and then so now we have the setup, and we can then prove the theorem very easily. So it turns out there are many systems you can take, right? You can take A, B, C, and D. You can have 4 systems, and you can make very complicated states, because the state could have a little bit of this psi1 times chi1 plus psi times some, chi3, and you can mix all the states in very complicated ways, and you can have a lot of fun with this. So people have been writing thousands of papers and books about all the different relations you can find of this kind. See, we said if there are two systems like this and they are entangled with each other but not with anything else, entanglement entropy of this with this is equal to entanglement of this with this, right? So there are little theorems like this you can find, and then there are, this again the definition of the entanglement. But now, so what is S of A? When I write entanglement of A, it means write A as entangled with everything else. So you take some state of psi1 of A and some state chi1 of all the rest, B, C, D, plus psi2 of A times some other state chi2 of B, C, D. And if there are two terms in the sum, then S of A will be equal to log 2, right? So that's the meaning of S of A. And so if I write S of A plus B, what does that mean? It means how is the total system A plus B entangled with the rest? The rest means C plus D. So that's the symbol here. If you say S of some system A, it means complete the entanglement of A with everything else. If you see S of A plus B, it means take the entanglement of A plus B with everything else, and so on. So the total system, I'll think, has not entangled with anything else. We can already start seeing some interesting relations, right? S of A plus B is S of C plus D. Is that obvious, right? Because when two things are entangled with each other, then the entanglement of is A plus B is with C plus D, but C plus D is with A plus B, so they are equal. So there are some nice inequalities, and the one we'll actually be using is what's called strong subadditivity, and it says that if we have 4 guys entangled with each other like this, then entanglement of A plus B with the rest, if you add to that the entanglement of B plus C with the rest, it's bigger than entanglement of S of A with BCD, entanglement of C with BCD. So right now it doesn't seem to make any sense. I mean, there's no intuitive way to see this very easily as to what this means, but it is one theorem. Out of all the theorems that you can make out of entanglement entropy, actually this is the one which is most difficult to prove. It doesn't have any elementary proof. It was proved around 1965 by Lieb and Ruskay, and the proof itself goes about 10 to 15 pages, so we won't actually try to prove it here, but we'll use it. It's one of the properties of entanglement entropy, but this is the one which will tell us that you can't actually make those delicate correlations and encode that all the entanglement and solve the problem of taking lots of Hawking pairs and removing the difficulty. Okay, so now we'll just go through the proof of the theorem in a few steps. So all we have to do is to take that theorem, and we have to find different sets A, B, C, D here, and then we'll get some inequality. And the inequality will tell us, look, you can't actually remove the entanglement. That's what we are trying to do. So we go back to our physical picture, find the systems A, B, C, D appropriately, and just plug into the theorem. Okay, so let's look at the picture. Here's our model. Step A, outside the black hole, let's say R greater than 10m, we had drawn dividing line here, right? Then we'll assume there's normal physics here. Does it look reasonable to you? Once you're outside 10m, let's not do anything funny. So look, I've put normal physics here. Okay. Inside the horizon, the particles which are deep in the hole, well, looks like normal physics here, right? This is like I can choose to be R equal to m. It's nowhere near the singularity. It's probably completely normal physics here. But actually, I'm not going to use any property of it. So why don't we just allow random things to happen here? I don't even care. So I just said, okay, I don't care. No claim about the physics here. We have to make as strong a theorem as possible. It's around here near the horizon we say that physics is close to normal. What does close to normal mean? In classical physics, we had the leading order Hawking calculation of quantum fields on curved space. It gave us the entangled pair 0, 0 plus 1, 1. And we said there can be small corrections. That's what we are trying to explore. So here we could put an epsilon times 0, 0 minus 1, 1 or some correction to Hawking's thing. I'll do that over here, and there'll be no other input into the problem. Okay, good. So as we said, near the horizon there can be a small correction, and here the normal space-time thing is only some approximation. We don't need anything here, as we said on the previous slide, and here's normal physics. And as we evolve from one slice to the next slice, one pair will be created. Okay, so here we had a vacuum mode, it evolves here, it creates one pair. I'm just drawing again in pictures what we have already seen 10 minutes ago. Okay, and so this will be a Hawking pair to leading order, but there will be small corrections. So this will be our notation. Let's set up some notation. These guys we don't care about, but remember C1 was here entangled with B1, C2 was here entangled with B2, and Cn was here entangled with Bn. So all the particles outside, this one came out first, so it's called B1, this is called B2. Then let's say n particles have come out, that's Bn. I'll call them collectively as a set B. These are the guys outside. Does that make sense? Okay. And all the guys which fell inside, I can call them collectively the set C, C1, C2 up to Cn. And the new pair I'm creating, I'll call it Bn plus 1 and Cn plus 1. Okay, so that's my cartoon picture. And I'm going to try to make the sets capital A, capital B, capital C, capital E to put into the theorem out of these animals up there on the board. So what happens at step n? At step n, up to step n, some particle pairs have come out, C1 entangled with B1, C2 with B2, and so on. And there can be small corrections, and there are Cn with Bn. Remember, this set was called B. This is my dividing line, everything same as before. And this is our notation. S of some set A is entanglement of the set A with the rest of the system. I'm just reviewing all the notation we have taken. And what we want to compute is the entanglement of the outside with whatever is inside. Okay? And so what's the entropy in all this at step n? At step n means when n particles have come out, it's just the entanglement of this set of guys outside with the rest. I'm not saying anything about how big it is. This is just a definition because by definition, right? The entanglement of this, I'm calling it Sn. At step n, the entanglement of the set B with everything else is the entanglement of the outside with the inside. This is all set up, so no physics right now. Not even any math right now. It's only notations. Now starts the physics. When a new pair is created out here, up to here is still the inside because this is all nowhere near 10m. The outside is the same. At this stage, the entanglement of the outside after step n, even though a pair has been created here, actually it remains the same. Why is it the same? Because suppose I have two different systems, one is here and one is here. This is the outside and that's the inside. Suppose nothing changes here, but something changes internally there. Will the entanglement of this with that change? Well, the answer is no. See, if I have psi1 times chi1 plus psi2 times chi2, And the chi1 and chi2, suppose they have some evolution. The chi2 becomes chi1 becomes chi2. Suppose they have some 180 degree rotation among themselves. Okay? It is still psi1 with chi1, psi1 with something and chi1 with something. There's still two terms in the sum. So it's a basic theorem that if you do a unitary operation of internally on some system, then the entanglement of the remainder with that doesn't change. Instead of being psi1 with chi1 and psi2 with chi2, it will become psi1 with some chi1 prime and psi2 with some chi2 prime, but there's still two terms in the sum. So the thing doesn't change. Okay? So I can create a new pair, but the entanglement of the outside with the inside actually hasn't changed. So even at this step, Sn remains the S of the outside, guys. Okay. Now let's talk about the pair which we have created. The pair itself is in the state 0 of Bn plus 1, 0 of Cn plus 1, 1 of Bn plus 1, 1 of Cn. This is the leading order Hawking pair, so there I just wrote the leading order answer. Let's talk about this guy's entanglements. You can see this guy Bn plus 1 is entangled with Cn plus 1. Right? Because it is 0, if that is 0, it is 1, if that is 1. Okay, just like a singlet. So what's the entanglement of the whole pair with anything else? It is 0, because the whole thing forms a state, but doesn't depend on anybody else. Right? So if you take B and C together, it's not entangled with anybody. So if I take the complete system made of B and C, is entangled with anything else is 0. It's already in one definite state. It doesn't care about the rest of the system. But if you look at the entanglement of only Bn plus 1 or Cn plus 1, actually I'm going to use the Cn plus 1 also in a minute, so let me write that. How much is the entanglement entropy of just Bn plus 1? Well, that is log 2, because you can see from that expression, this particle Bn plus 1 is entangled with this Cn plus 1 in this way, with only two terms in the sum. So the entanglement of Bn plus 1, if I take only this system, it's log 2, because entangled with Cn plus 1, and S of Cn plus 1 is also log 2. It's very elementary. There's just two guys entangled with each other, and they don't care about the rest of the system. So at leading order, these are the answers. So let's see if everybody is okay with these two numbers. And also the same thing for C, which I forgot to write on the screen. Now let's put in the small corrections. Because if you make small corrections, this number was 0 to leading order. Let's say it has to be less than some small number epsilon 1 even after I put my corrections. Does that sound reasonable? The entanglement of Cn plus 1 was log 2 at leading order. It can decrease. So let's say it decreases but doesn't become less than log 2 minus epsilon 2, and epsilon 2 is small again. Now I have put in my small corrections. So I'm saying at leading order, this guy still has to be log 2 almost, can't be too small. And this guy was 0 at leading order, it can't be too big. This is my definition of small corrections. This is all I'm going to put in. And so everybody was happy with this. People are happy to believe this. What they were wondering was, because the number n will become larger and larger, will I be able to change the entanglement? And we want to see, no, that we can't. So what's the entanglement entropy at step n plus 1? Now we are coming to the crucial physics, because now what's going to happen is the pair we made here, under stretching, one guy goes out. It's been Hawking radiated. Now the members B outside has B1 to Bn, which we had called the set B, but this guy is also outside. So if I want the entanglement at step n plus 1 between the outside and inside, it's the entanglement of all these guys with what's inside. So entanglement entropy of step n plus 1 will be the entanglement of this set B plus Bn plus 1. All these guys with everything else. You agree we have to write it like this. So you can see how in the inequalities we had S of A plus B, S of C plus D all coming in. Now you can see I'm just putting everything in that language. So at step n plus 1 I have these guys and this. All these together make a set, the old set B plus Bn plus 1. That with the rest is the entanglement of the outside with inside at step n plus 1. And what am I trying to prove? I'm trying to prove that Sn plus 1 is always bigger than Sn. If that is true, the entanglement keeps growing and growing. It's not going to come down, and then I'm finished. Okay, so that's where I'm trying to go. So far, it's mostly notation. I'm just putting everything in there. And now in one step, we have the entire theorem. So everything else I'm going to tell you is right here, and then we are actually indeed done. This was the strong similarity inequality. Okay, so let's put it up here. Now let's define all the sets. The set A will be the set B. What was B? These quanta, which was initially outside. That's the set B. Oops. The set B is just one guy, Bn plus 1. The set C in the inequality with just one guy, this particle Cn plus 1. And remember, S at step n was given by S of B. S step n plus 1 was S of B plus, both these guys were outside. So this was this. And these were the other inequalities. This was 0 at leading order, so we say it's not too big at the next order. This was log 2 at leading order. It can't be less than, we said, this at the next order. These are my small corrections. Everything is here. Well, let's put this in this theorem. If I put A, B, C, D, I'll give you a minute to check that I put my A, B, C's correctly in here. And from there, I'll give you a second to check that this is true. Okay, so people check that these numbers are exactly these numbers, and then you plug them in here. This is what we call Sn plus 1, this is Sn. And so with the fiddling around with this theorem, which is actually rather non-trivial to prove, but once you accept that theorem, you can actually prove the entanglement step n plus 1 is bigger than Sn plus log 2. In leading order, Hawking found Sn plus 1 is Sn plus log 2. But if you put small corrections to each pair, you can now prove how many pairs are being emitted doesn't matter. At each step, the entanglement just actually keeps going up. By log 2, at most, it gets decreased by a small amount, epsilon 1 plus epsilon 2. So if you draw this in pictures, you see the entanglement will keep rising. Small corrections cannot make it turn around and go down like a normal body. So it tells you that the Hawking argument is stable against all small corrections. So even though Hawking just gave a rough leading order calculation in 1975, for all these years people had been thinking maybe there's some subtle way of encoding information in the Hawking radiation. So people tried things like saying if one particle goes out now, the temperature of the black hole slightly changes, so next particle is slightly affected, and that could have a little bit of correlations, and some correlations hiding among so many particles can get the information out. Now in one shot we know that none of those things was correct. Okay, so now we have in fact a very serious problem, because now, okay, I just exited out of this, give me a second. So now we have a very serious problem, because now we see that we have to change the black hole structure completely. If the black hole structure stays anywhere close to normal physics, we can add any small quantum fluctuations or any other source of physics, as long as the physics is small, let's say 1%. The total entanglement you can reduce is at most 2%, right? Suppose these were 1% each, then you can get down at most 2%. And so the entanglement, instead of growing by this amount, will go like just slightly lower than that, but still keeps growing. So you can't solve the problem. And so this is telling you the Hawking argument is completely rigorous against all sources of small corrections. You either change the horizon completely, or you accept that quantum mechanics is destroyed, or you accept remnants, which you can't do in string theory, or you do something, third thing, which is completely different. Okay. So now this just sets the stage for what we want to do tomorrow. So on Monday, what we'll try to argue is that in string theory, as we said, we can't get remnants, we don't want to lose information, and this tells us that the Hawking argument is completely rigorous now. And so what we're going to do is we'll go to string theory and actually see if you try to make a black hole, what do you get? And we see that if you try to make a black hole, you just can't. These guys just keep becoming bound states, which put more particles, say, okay, now I can make a black hole, put more particles saying, now I can make a black hole. You never can. The size of the bound state just keeps swelling up and always becomes horizon size. Okay, so once we understand a little bit about how that happens, we'll actually see a simple case where you can see how you do the calculation, see how that comes out. Then you see that in string theory it's a whole different solution, but then you have to go back and ask, how do you beat all those no-hair theorems? We were seeing that just can't hold anything there. Everything wants to fall in. It was so easy to make a black hole. We want to see what are the special properties of having a theory with these extended objects, and what do you do with the geometry so do you actually beat things like the Bugdal theorem. It's very interesting how they all get circumvented, and the actual bound state string theory don't make horizons. Okay, so let me stop here. Thank you. Questions? Yes.
So the initial argument was that there was some idea that through the addition of many small corrections, this may add up to overcome the leading term.
Yes.
But here, in the inequalities, there is a good argument that the correction can't be larger than
yes. So
large enough to
that's exactly what we are saying. The original thing that people were thinking was that the small correction at each step might have some cumulative effect to remove the entanglement by the time a lot of particles have come out. But what we are proving here is that is not true. The small effect do not actually accumulate in that way.
So the reason that we can constrain the entropy here is because is the difference between the individual corrections and the cumulative corrections.
Yeah, that's what we are trying to do. So at individual steps, we have assumed that there can be, let's say, a 1% correction, let the epsilon be 0.01. So at each individual step, we have allowed the correction. And what we are trying to see is there some way to constrain the total entropy after 100 particles have come out, 100 outside, 100 inside? Is there some way to constrain the fact, suppose in this inequality, I got here n times epsilon 1 plus epsilon 2. Suppose that's the best I could do. In fact, most of the inequalities you get among entropy inequalities you get in a typical textbook will actually be proportional to n, the number of particles also, or some power of n. Okay? Then you actually can't prove anything, because n is going to become bigger and bigger for big black holes. Epsilon can be smaller and smaller because it's become more and more classical for big black holes. But n times epsilon can remain order 1, and then you can say, hey, it's completely gone. I can't prove anything. So it is important to get some inequality where this does not have any epsilon, any power of n multiplying it. And if you try to use any other inequalities from quantum information theory, you typically always find some positive power of n here. But if you use a strong subroutine inequality, then you find you can actually do it with no power of n, and then you're really good. Then you're good. Because n times epsilon can be order 1. We can't stop that because n is a big number. But just epsilon has to be small because we are in a classical black hole situation. So any small correction we are allowed. Otherwise, you have to say the classical black hole is completely gone. That's the point here. Yes?
So how about the states of creation of 2 pairs or 3 pairs, etc.?
You mean?
They can be, for example, epsilon 3, epsilon 4, and things like that.
Yes, so let's see what you're asking. So here, of course, I'm creating many pairs, right? This is the C1, B1 is the first pair, C2, B2 is the second pair, and so on, right? So there are many pairs here. That's what we are dealing with, right? And what we are saying is that if C1, B1 came out in some state, the state of C2, B2, we are allowing it to be influenced by the first guy, right? Because that's what we had said. Each pair can depend a little bit on the other pair to cross-correlate. Let me see where I drew that. Right, so if at the first step, the pair B1, C1, suppose it came out in 0, 0, or it could have come out in 1, 1. If it came out in 0, 0, the second pair state I'm changing in one way. If it came out as 1, 1, the second pair, the B2, C2, I'm changing in a different way. See, I made epsilons into epsilon primes. So I can make different, the second pair can depend on the first pair. I'm allowing all that. So that's what subtle correlations would mean, right? That what the second pair will do a little bit different depending on what the first pair did. So I'm encoding all those as a small corrections. I'm allowing all those possibilities. But even that, even though the number of correction terms is very big, you can still make the inequality in such a way by going through these theorems that the total entanglement actually doesn't pick up the effect of n. The effect of n being large is not picked up.
And the state of, for example, 2, 2, can be separated.
Oh, 2, 2, you mean 0, 0 plus 1, 1 plus 2, 2. You mean that kind of entanglement. Oh, that's what you were asking. Yeah, so people have done that by now. I had a student called Steve Avery who did with 4 steps. Like he allowed not just binaries of 0, 1, he allowed actually 4 steps. And it's actually immediately generalized. It doesn't have to do with just using 2 steps. You can do it with any number. Yeah. Okay, more questions? Okay, good.